Azevedo. And the next three talks now, I believe they are all on optimization of structures. Okay, all right, thank you very much.
Okay, as announced, I'm Felipe Miranda Azevedo. I'm here to present about evolutionary topology optimization for acoustic mufflers. I'm doing this research under Professor Pavanello. And well, let's start. Well, here's the summary of some topics I'm going to be talking about in this presentation. And I'm first going to start with context and motivation, then going to go through objectives, analytical and approximated transmission loss in a muffler, muffler device, evolutionary acoustic optimization problem, then numerical results, conclusions, and then acknowledgements. Well, first of all, for context and motivation. Well, as we all know, a great portion of the noise produced in urban centers comes from automobile engines and exhaust pipes. So it's a great deal of noise being produced by those systems, let's say like that. And these noise levels have been object to several studies since new regulations are constantly being enforced nowadays. As we all know. So new manufacturing technologies and materials for noise cancellation were developed in recent years in order to respect the noise levels imposed. So technologies like active noise cancelling and new materials, superficial, like clothing, and so on. So one of the devices in scope for reducing noise levels are the silencers installed at the end of automobile exhaust pipes. They are silencer or mufflers, and they are expansion chambers that increase sound transmission loss in the muffler or exhaust pipe of the automobile. So still in context and motivation, muffler or silencer has a function. It has acoustic purposes only. Although it can damage functions like flow or thermically speaking. It creates a sound decreasing zone by increasing transmission loss, what we call TL. So its geometry has several configurations depending on the automobile which is installed in, but generally it can be represented by a cylinder with perforated ducts crossing from inlet to outlet, from one side to another. This is the simple model that we're going to use throughout our research. So objectives. Our main objectives are to develop mufflers with increased transmission loss using evolutionary structure optimization approach. And to verify the efficiency of the topologies found with the ESO approach. So analytical and approximate transmission loss in a muffler. So for analytical transmission loss in a muffler, we can use the following equation, which we can see that's a logarithmic equation, function of the fraction of diameters of the expansion chamber, the acoustic chamber, and the inlet and outlet diameters, as you see in M. And also function of K, which is the wave number, and L, which is the length of the acoustic chamber. This is an analytical equation. It's common in literature to use that. It's only used for expansion chambers without any barriers inside, like the model we're showing here in this picture.
And what is C?
C is the velocity of sound in the medium, which is air. Okay, so for approximate transmission loss, using the finite element method. For that, we're going to use the three-pole method, which is represented by this equation here. It's a function of P1, P2, and P3, which are sound pressure levels in point 1, point 2, and point 3 in the inlet and outlet. And the exponential of the imaginary wave number times the distance between P1 and P2, which is L. Okay, this is used because of what I mentioned before. As we are doing the optimization process, we're gonna fill this expansion or acoustic chamber with rigid elements. So our analytic equation won't be valid anymore. So we need to use this three-pole method approach. So our muffler device, governing equation, and finite element model. So the governing equation of the system we're studying is the Helmholtz equation. We can see it here in equation 4. As commonly known, this is the Laplacian operator here. Frequency squared and velocity of sound in medium squared, and pressures, sound pressures. Okay, this problem here we'll have 3 different boundary conditions. We'll have Vn, which is a particle velocity, which is going to be used in the inlet of the muffler. We're going to set that to 1, and also we're going to have an impedance in the outlet, which we're going to set to rho times C. That is going to be our boundary condition to simulate an open condition, an open air condition. Okay, so here we can see our design domain. It's fluid domain, inlet boundary condition, outlet boundary condition, and here we have the rigid wall boundary conditions, which encloses our muffler, right? There's inlet, outlet, and the boundary the sidewalls. We have the fluid domain, and we also have our design domain. We're not gonna do our optimization process in the entire fluid domain. We're gonna only use this section here on top and this section here on the bottom, so that we won't interfere with the flow of the exhaust gases. Okay, all right. So using the Helmholtz equation with the finite element method approach, we're going to reach this, this system response equation here, equation 7, which is composed by K, it's a stiffness matrix, C, which is a damping matrix relative to our impedance, our second boundary condition, our mass matrix, P is the pressure, sound pressures vector, and VNI, which is a vector of the imposed condition on the inlet. Okay, here we can see how to assemble and to calculate all the matrices, and remembering that B is the derivative of the shape functions used in the finite element method, and N are the shape functions themselves. Okay, all right. So using both approaches, analytical and FEM approximated, we can see that in this curve, red is FEM and blue is analytical. They're very approximate. And for larger frequencies, as long as the frequency goes up, our method kind of deviates a little. Okay, evolutionary acoustic optimization problem for transmission loss maximization. It's the problem, this is the research we're doing. So our problem statement is to maximize transmission loss, which is represented by this equation, subject to our system response equation, and volume constraints, where our design variable xy will be 0 or 1, which means 1 for a fluid element and 0 for a rigid element. So as we optimize our system, we'll have elements filled with fluid being switched by empty elements. Those are going to represent our rigid barriers being created in our muffler. Okay, for our optimization process to work, we need a gradient-based optimizer. Our gradient-based optimizer is the derivative of our optimization function. So the derivative of TL with response to our design variable is going to be this equation here, where Pn is the relationship between pressure 1 and pressure 2. And P3, P out is the pressure in point 3. Okay, numerical results. So for our optimization process, we used an evolutionary ratio of 0.16666%, which is the rate of going to remove elements from our domain. So we're going to be removing 0.16% each iteration until we reach a final volume of 97%, which means we'll have 3% of rigid elements in our entire domain. We're going to be using optimizing our system. We're going to be optimizing our system for 4 different frequencies. They represent peak and valley frequencies, which can be seen in that curve I showed you before. Those are TL peaks and TL valleys on that curve. We can see here 346 Hertz, 693 Hertz are valley frequencies, which approximates 0 in that curve I showed you before. And 173 Hertz and 519.5 Hertz are the peak values of transmission loss, which are approximate 8 decibels. Okay, for valley frequencies, we had this couple of topologies here, where topology A is represented by this dotted black line here for a range of frequencies, and topology B is represented by the black thick line here. We can see that optimization process here worked pretty well, since TL was raised from 0 to from 0 because they're valley frequencies. So the whole curve here, it's increased. The whole curve here went up, so it's a good optimization for that set range of frequencies. We can see here in the thin black line, this is the nominal muffler. So the curve was set to be like this, and now it's the black line, thick line, or the dotted line. So for the for this range of frequencies, the optimization, was successful. And for peak frequencies, which are 173 Hertz and 519.5 Hertz, we reached this topology and this topology. For a range of frequencies, we have this set of data here, which black thick line is the topology for muffler D, and the black dotted line is topology C, right? So because my graph here is not in the same scale here, we can't actually see that the topology here, the optimization process here was better or equal to the one I showed before. But seeing closely, we can tell that the optimization process here went a little better. So for valley frequencies, we had a better optimization process than for peak frequencies, just a little better. Okay, and the conclusions. The results presented here show the capability of the proposed methodology to maximize noise attenuation in the studied system, as I showed before. The optimization process for valley frequencies produced topologies with better efficiency for a range of frequencies. I think that's switched, I think. And final topologies presented in this work, although a little different from the ones presented in the literature, show the same structural range and the same TL range, which means the topologies I presented here converge to the same type of topology we're going to find in the literature. And the TL trend, I mean, the transmission loss we found here in this optimization process was the same found or approximate to the ones found in the literature. Okay, acknowledgements. The others here are grateful for FAPESP and copies for our financial, for the financial support of this work. Thank you.
Questions? I have one question. Somebody have? I have one question.
Okay.
I think I missed perhaps an important point.
Okay.
It's not. What is actually being optimized? I think this is the whole talk.
Okay. It's transmission loss. Transmission loss is the capacity.
What do you optimize? The geometry, the dimensions of the muffler?
No, I'm adding or removing. Yeah. Yeah.
But what function?
TL, transmission loss. Transmission loss. I'm optimizing this equation right here. I'm maximizing TL.
But what is that? What physical property are you changing to maximize this function?
Okay.
That's
Okay. I'm introducing rigid elements in our domain so that our maximum TL, our TL gets higher.
Okay, so that these are fixed structures that you insert inside the chamber.
Yes, exactly. So we start the process with the empty chamber. We start the process with an empty chamber, and as we go through, we remove fluid elements, which means we're adding small elements, rigid elements, and then we maximize TL doing that.
But your silence in your car is made with a central tube with the
Perforated.
holes and some barriers.
There it is, yes.
Okay. And when they put a horizontal line, black line, it means that in this region,
Yes.
the perforated tube must be closed. And when they put, sorry, the vertical lines is a barrier, closed line. And here it's finding the best place for each frequency or different frequencies.
Sorry if it was not clear
I
enough.
understand everything. Yes, the function and the optimized function, but I didn't understand which physical structure was going into the
Okay.
function to be optimized. So
Uh,
these are where to place the barriers.
Yes, yes. Some other question? Oh, Labaki?
What's the acoustic part of it?
What?
There's also an acoustic part involved that I missed.
Well, transmission loss is a function of the pressure, sound pressures. So when I increase transmission loss, what means is the difference between the pressure sound in the inlet and the pressure sound in the outlet is going to be bigger. So in the inlet, I'll be having like 7 decibels, for example. In the outlet, I'll have like 5. So the bigger the TL gets, the smaller the outlet sound pressure will get. So that's our goal. Was that clear?
Yeah.
Okay.
What kind of applications do you imagine for this in the
What?
future? What kind of applications for this you imagine in the future you can provide?
Okay. First, this is a preliminary study.
Yeah.
So later on, we'll implement fluid equivalent elements and porosity, so that we can model our muffler better. We can better model our muffler, and then we'll try to experiment and see, because all the mufflers that there is were made and studied by Moon Zhao a long time ago. So this optimization process is quite recent. So we're trying to reach, basically we're trying to reach same topologies that there are now and to create new topologies for the mufflers in the industry. So later on, we're gonna try and reach a topology that is better than the ones that already is.
This is just a curiosity. So,
Okay.
where does the noise come from? I mean, of course, from the moving parts of the engine, but also from the flowing of the gas
Yes.
in the pipes, like a fluid.
Yes, the muffler, well, the exhaust pipe is divided in two parts, the hot zone and what we call cold zone. Here we're working with the cold zone, which is acoustic purpose only. The hot zone will work with filtering the gases and so on. But the vibration of the engine, that frequency, that sound will come through all the two parts, and here in the muffler we'll try to decrease that level, the sound level.
Okay, so the main factor is the vibration of the engine, not the flowing of the... I mean, because if you blow some air into a flute, it's going to make noise. So
Yes.
I'm trying just to understand. So the biggest part of the noise comes from the engine,
The
not
engine.
from the flow of the air on the exhaust
Yes.
pipe, right?
Yes, we have some features that the air will go through the pipes, and they will make different sounds.
Yeah.
But the main part is the engine.
Yeah, the people that tune cars also have more noise on their...
Yeah, depends.
Then I'm confused.
Okay.
I thought that this was some sort of the frequency that you're going to use there, it has to do with the frequency of the injection of the gas by the engine, not the vibration of the engine block itself. It has nothing to do with the block.
No, it's not the vibration of the block, but
it's the expulsion of the gas that's pulsed.
In fact, I don't know the response, but I guess that there are some effects. There are the flow effects. There are the oscillation of the
pistons,
There are
explosions.
also the vibration of
The muffler
shell
pipes.
itself, because they vibrate a lot also. There are a lot of sources of vibration. I'm not sure.
Yeah, there's not. I don't think there is only one type of sound coming through. It's a very good question, actually.
Any more?
Oh, we had a question here and there. Oh, she can ask first. Get you.
One question is just for curiosity. Is there any difference in the radius of the inlet and outlet? Because you are using the same radius,
Yes.
in this market.
Yes, there is a difference. There is studies for muffler shape, which they optimize the lengths and the diameter, but that makes difference. Okay.
So you are just changing the place where you put that structure inside the chamber, or can you change the structure itself?
Well, this is not a fixed structure. So as the optimization process goes through, we're gonna be removing fluid elements, and that's gonna be based on our sensitivity analysis. So this structure here was made purely by that. It's not a fixed structure that I'm moving through our expansion chamber. So I didn't put the picture, but the barrier starts here, and it keeps growing till it reaches the middle, and then starts doing this portion here horizontally.
So you begin with nothing inside the chamber?
Nothing inside the chamber. Yes. Yes.
It's interesting that the solution is always constructible. You could build a muffler directly with that structure that can vary the position according to the frequency there.
What do you
Because
mean?
like, it's the optimization process, but the final geometry is always the same.
It's very close.
According to the frequency, right?
Yeah, kind of, but we can see here that it's very. Yeah, it's very close. It's very close actually. But there is frequencies that we can have 2 barriers instead of 1.
Okay.
So it varies a lot. So, and this is the SO method. It's a simpler preliminary method to the BSO, which is the one my colleague Claudio would explain later. Okay, Professor?
I think we choose to put not too much material in the barrier, just 3%.
3%.
Until we allow to continue the optimization method, we can found different
Different yeah.
But in the real application, they put
Little.
only
different solutions. And that's purely because of a mass restriction. Because the muffler pipe is only restricted by a couple of wires in your car, so it vibrates a lot. If you increase that mass too much, then it will vibrate more, and so on, and then it won't be valid anymore. Okay?
All right.
Thank you.
Thank you very much.